Let's discuss the next topic. This is on adjoint and inverse of a matrix. Let's say we have matrix A. It's a 2 by 2 order matrix. Elements A, B, C, and D. We know how to find out cofactors. Let's write cofactors with capital C's. C11. This means it's cofactor of element A11, and element A11 here is A. That is A. And what is this equal to? This is equal to minus 1 raised by 1 plus 1 into determinant of the minor. So for that we leave this row containing element A and column containing element A. So that's D. Determinant of D is D minus 1 whole square. So this is D. Similarly, we can find out cofactors of remaining elements of the matrix. C12, that's cofactor of element A12, that's B. And this is minus 1 raised by 1 plus 2 into determinant, leave row containing B, column containing B. Whatever is left, that is C, determinant of C. So this is minus C. This is next minus 1 raised by 2 plus 1 into determinant of B. So this is minus B. And minus 1 raised by, this is 2 plus 2. Leave this row and this column, determinant of A. So minus 1 raised by 4 is plus 1, so this is it. Now let us understand what is cofactor matrix. So we write C is cofactor matrix. We have to replace each element of A by respective cofactor. So that means in place of A, we'll write D. In place of B, it's minus C. And minus B here, and this is it. This is cofactor matrix. Matrix obtained by replacing each element of matrix A by respective cofactors. So this is cofactor matrix. So what is adjoint of A? Adjoint of A is transpose of the cofactor matrix. So transpose of this means interchange rows and columns. D minus C becomes the first column. Second row minus BA becomes the second column. This is adjoint of A. So we can see for a 2 by 2 order matrix, we can directly write adjoint of A by interchanging the diagonal elements. So interchanging the diagonal elements. And what about non-diagonal elements? We change sign of non-diagonal elements to get adjoint of A. Next is inverse. So let us first of all find out determinant of A. Determinant of A here is A into D minus B into C. That's AD minus BC. Let us recall what is a singular matrix. So matrix is singular if value of determinant is 0. So if determinant of A is 0, we have singular matrix. A matrix is invertible. A matrix has inverse, that is A inverse exists if A is a non-singular matrix. A is a non-singular matrix. That means determinant of A, this should not be equal to 0. For the inverse to exist, matrix should be a non-singular matrix. That is, determinant of A is not equal to 0. And what exactly is inverse of A? This is defined adjoint of A upon determinant of A. So that is why determinant of A should not be equal to 0, because determinant of A is in the denominator. So if this is a non-singular matrix, then we can write adjoint of A upon determinant of A. We write 1 upon AD minus BC, this is determinant of A, into adjoint of A. This is minus C into this is C. So this is how we find out inverse of A. Now adjoints and inverses have properties. Let's go through. The first one is A into adjoint of A. This is equal to determinant of A into I is equal to adjoint of A into A. The second one, inverse of A inverses A. Next is A into B inverse. This is B inverse into A inverse. This is called reversal law. This is reversal law of inverses. So we know reversal law for transposes also. This is reversal law for inverses. A into B inverses, B inverse into A inverse. If there are three matrices, let's say A, B, C, A into B into C inverse, this is equal to, so C inverse into B inverse into A inverse. So in words, can we say inverse of product, inverse of ABC, this is product, inverse of product, this is equal to, this is product of inverses, product of inverse of C, then of B, then of A. So inverse of product is product of inverses taken in reverse order. We have reversed the order. So third matrix, then second matrix, then first matrix. Next property, A transpose inverse is same as A inverse transpose. Next, determinant of adjoint of A is equal to determinant of A raised by n minus 1. What is n here? N is order of the matrix. Obviously, we have square matrices here. Then adjoint of A transpose is adjoint of A whole transpose, and adjoint of A, this is equal to determinant of A raised by n minus 2 into A. Let us for this given matrix say find out cofactors. So we write C11. This is cofactor of element A11. So A11 is this element. This is A12 element on the first row, second column. This is A13. These are elements of the second row, third row. This is 3, 3. So C11, this is minus 1 raised by 1 plus 1 into determinant. Now leave this row and this column. We are left with these 4. This is minus 1, 5. This is minus 2 and this is 3. This is minus 1 raised by 2 is plus 1. So minus 3 and plus 10. That's 7. C12. 1 plus 2 into, for this, leave this row and this column. We are left with 0, 5, 4 and 3. This is 4 and this is 3. This will be 0 minus 20 into this minus 1, so plus 20. Similarly, we can write cofactors of other elements. C13 minus 1 raised by 1 plus 3 is 4. 0 minus 1, 4 minus 2. This will be 0, this is plus 4. C, these are now elements of second row, cofactor of this element. This will be minus 1 raised by 3, which is minus 1, into determinant. Leave this row and this column. This is minus 2 and this is 3. So this is minus 1 into, this is 3 minus 6. So it's 3. C2, 2. This is minus 1 raised to 4 is plus 1. So this is determinant 2 minus 3, 4 and 3. That's 6 plus 12. It's 18. Next, this will be 2, 3. This will be minus 1. This is the element at the intersection of second row and third column. So we are left with leaving this and this 2, 1, 4 and minus 2. This is 4 and this is minus 2. So minus 4 is minus 8 into minus 1. Then C3, 1. This is minus 1 raised to 3 plus 1 is 4 into determinant. This is element. Leave this row and this column. Determinant of this part, which is 1 minus 3 minus 1 5. Minus 1 is for 4. This is positive. This is 5 minus 3. Similarly, this is minus 1. 3 plus 2, it's 5. So that's minus 1. Then for this, leave this and this. We have 2 minus 3. This is 0 and this is 5. And for the last element, this will be determinant 2, 1, 0 and minus 1. That's minus 2. So we have cofactors now of all the 9 elements of the matrix. We can, so this part is done. We have to write the cofactor matrix. This is cofactor matrix. We replace each element by cofactor. So cofactors of elements of the first row, this is 7, next is 20 and then 4. 3, then 18, this is 8 and then we have 2, minus 10 and minus 2. So this is cofactor matrix. Next is adjoint of A. Adjoint of A is transpose of this. Transpose means interchange rows and columns. First row is now the first column. Second row is the second column. Third row. So this is adjoint of A. Next, we have to find out determinant of A. So we have matrix A, determinant of A. We can expand along elements of the first row, or first column. This is 2 into, it's minus 3 plus 10 plus 4 into, it's 5 minus 3. That's 7 into 2, 14. And this is 22. So can we say it's a non-singular matrix? Yes, it is a non-singular matrix because determinant of A is not equal to 0. Since determinant of A is not equal to 0, therefore A is a non-singular matrix. This is a non-singular matrix. What about inverse of A? A inverse is, we know, adjoint of A upon determinant of A. So A inverse is 1 upon this is determinant. Determinant is 22 into adjoint of A. Let's rewrite. A inverse is adjoint of A upon determinant of A. This is determinant of A. This is adjoint of A. 7, 3, 2. 18, this is minus 10, 4, this is 8 and this is minus 2. So this is inverse of A. Let us now verify this result, that A into A inverse is I. So A into A inverse, matrix A, that's 2, 1, minus 3, 0, minus 1, 5, 4, minus 2, 3. This is inverse. This will be 7, 3, this is 2, 20, 18, minus 10. This is elements of the third row. Let's write 1 by 22 outside. So we multiply first of all elements of first row and here first column. This is 14, 2 into 7 plus 1 into 20 and minus 3 into 4, that's minus 12. Next element 2 into 3, that's 6, it's plus 18 and minus this is 24. Then 2 into 2 is 4, minus 10 and plus 6. Similarly, we get elements of the second row. So second row multiplied by first column, then by second column, then by third column. This is 0 into 7, minus 1 into 20, 5 into 4 is plus 20. This is 0, then minus 18, 5 into 8 is plus 40. Next is 0, this is 10, 5 into 2, minus 10. Then elements of the third row, this is 28, minus this is 40 and this is 12. Then 4 into 3 is 12. Then this is minus 36, 3 into 8 is plus 24. Next 4 into 2, 8 plus 20 and this is minus 6. Let's see what do we have. Is 1 by 22. This is 34 minus 12, it's 22. This is 0, this is 0. So we can see this is 0, this is 22, this is 0, this is 0, again 0 and this is 22. So this is 1 0 0, 0 1 0 and 0 0 1. This is I. So A into A inverse is I. This is true for every matrix A. A into A inverse is I. Next, let us verify this result that A into adjoint of A is equal to determinant of A into I. So let's write A into adjoint of A. This is the given matrix. 0, minus 1, this is 5, 4, minus 2 and 3. Into adjoint of A, this is 7, 3, 2, 20, 18 and minus 10, 4, 8 and minus 2. Let's multiply. It's 14 plus 20 and this is minus 12. Then 6 plus 18 minus 24. And next, that's 4 minus 10 and plus 6. Then next is this is 0 minus 20 plus 20, this is 0, 0. This is minus 18 plus 40, it's 22. Then 0, it's 10 minus 10, 0. Then 28 minus 40, this is 0, this is 0. 8 plus 20, 28 minus 6, this is 22. So this is 22 times 1 0 0, 0 1 0, 0 0 and 1. We are taking 22 common. And what is 22? 22 is value of determinant of A. So this is determinant of A and this is I. So A into adjoint of A is equal to determinant of A into I. Next part, we have to find out determinant of adjoint of A. Let's find out determinant of this part. 7, 3, this is 2. This is 18 minus 10, 4, 8 and this is minus 2. Let's expand. This is 7. It's minus 36 plus 80. Then minus 3. It's minus 40 and plus 40, that will be 0. Plus 2. It's this product 160 minus this, which is 72. So this is 7 into 44. This is 2 into, this is 88. This is 308. This is 176. So this is 484. And what is determinant of A? Determinant of A here is, determinant of A is 22. Determinant of A is for n minus 1. And here is order of matrix, which is 3. So 3 minus 1, this also 484. This is A and B. This is 2 by 2 order matrix, this is 2 by 2 order matrix. And we have to verify reversal law of inverses. That is, we have to verify A into B inverse. We know as B inverse into A inverse. So I repeat that inverse of product is product of inverses taken in reverse order. Let's find out determinant of A. This is 8 minus 18. That's minus 10. A is therefore a non-singular matrix. Value of determinant of A is non-zero. We can write now adjoint of A. We can interchange the diagonal elements 2 and 4, and we change sign of these. Minus 6 and this is minus 3. This is adjoint of A. Okay, in your board's exams, you are not to do this. Find out cofactors, write cofactor matrix, take transpose to find out adjoint of A. So this is adjoint of A. Let's write A inverse. It's 1 by determinant into this. This is minus 3 and 4. So this is the inverse of A. Let's find out now determinant of B. Determinant of B, this is 15 minus 14 and this is 1. Not equal to 0, therefore B is also a non-singular matrix. Let's write inverse of B. This will be 1 upon determinant into adjoint of B. Interchange diagonal elements. Change sign of non-diagonal elements. From A inverse and B inverse, we can find out the right hand side. Let's evaluate right hand side. Is B inverse into A inverse. This is B inverse. This is minus 7. This is 3 into A inverse. Let's write outside. Then this is 2 minus 6 minus 3. This is 4. This is minus 1 by 10. Now multiplying matrices. This is 10 and plus this is 16. Then minus 30 minus 8 minus 38. Then minus 14 minus 9 minus 23. And this is 42 plus 12. That's 54. So we can say it's 1 by 10 multiplying by minus sign. Minus 16 plus 38. This is 23 and this is minus 54. To evaluate left hand side, we need first of all A into B. Let's find out matrix AB. A into B, this will be 4, this is 6, 3 and 2, 3, 2, this is 7 and this is 5. This is 4 into 3, 12 plus 42. Then next, it's 8 plus 30 then it's 9 plus 14, 23. This is 6 plus 10, this is 16. Next, determinant of A into B. Determinant of matrix, let's find out AB. This will be this product minus this product. Let's learn how to multiply 23 into 38. Let's do it separately. Use this frequently. This can be written 20 plus 3 and this is 40 minus 2. 38 is 40 minus 2. We can easily multiply. This is 800. This is minus 40. This is plus 120 and minus 3 into minus 2 is minus 6. So this is 920 and this is 46. So 874. This is 864 minus 874. This is minus 10. Let's write now A into B inverse. This will be 1 by, this is determinant. So to find out adjoint means interchange the diagonal elements and change sign of these. This is minus 38 and this is minus 23. So you can see this is same as the right hand side. This is same as the right hand side. Left hand side same as the right hand side. This is how we get it. We prove reversal of inverses, that is we have proved A into B inverse is equal to B inverse into A inverse. Next, we are given matrix A. We have to verify a result. A square minus 4A plus I is equal to, this is null matrix O, this is not 0. Let's find out A square. Or let's write left hand side, it's A square minus 4A plus I. This is A into A. This is 2, 3, 1 and 2. Minus 4 into A. 2, 3, 1 and 2. And plus I. I is here 1, 0, 0 and this is 1. This is 4 plus 3, 7. 6 plus 6 is 12. 2 plus 2 is 4. 3 plus 4, 7. Multiply elements of this matrix by 4. This is 8, 12, 4. This is 8. This is 1, 0, 0 and 1. 7 plus 1 minus 8. This is 0. 12 minus 12. 4 minus 4. 7 plus 1 minus 8. This is an null matrix. Next, hence find A inverse. Hence find A inverse means we have to use the proved result to find out A inverse. We can otherwise find out A inverse. How do we do that? We know A inverse is adjoint of A upon determinant of A. We are not to use that. We are to hence find A inverse means we are to use this result to find out A inverse. Let us write the result. Proved. We just proved this is equal to a null matrix. Okay, here we multiply both sides by A inverse. A inverse into A square. Next, A inverse into A, then plus A inverse into I. This is A inverse into null matrix. A inverse into A square, this will be A. A inverse into A, this is I. And any matrix into I is matrix itself. So therefore this is A inverse. And what is any matrix multiplied by null matrix? We know it's null matrix. So this will give us A inverse as, shift these terms to the right hand side, 4i. This will be 4, 0, 0 and 4. I is identity matrix, 4i is a scalar matrix, minus A. This is 2, 3, then we have 1 and 2. This is minus 3, 0, minus 1. So this is A inverse. This is how we hence find out A inverse. Hence, I repeat, hence find A inverse means use the verified result to get value of A inverse. Okay. Next we have a matrix equation. We are given a matrix 2 by 2 order matrix into matrix A equal to right hand side, that is another 2 by 2 order matrix. So we can easily show that A is a 2 by 2 order matrix. Let's say this is matrix B, this is A, and this is, let's say this is C. We assume this is B and this is C. From this matrix equation, we have to find matrix A. We will get matrix A if we remove matrix B from the left hand side. So to remove matrix B from left hand side, we pre-multiply, that's right. We pre-multiply both sides by B inverse. B inverse into B into A. This is B inverse into C. Now by definition, B inverse into B is I, and any matrix into A is A. Sorry, I into A is A. This is B inverse into C. So we have C, we want B inverse. To find out B inverse, let's check determinant of B. Inverse exists if determinant is not equal to 0. Determinant of B is this minus this. It's 5 minus 4. This is 1, not equal to 0. So B inverse is adjoint of B upon determinant of B. So since determinant of B is 1, therefore B inverse is same as adjoint of B for this question. And what is the adjoint of B? Interchange the diagonal elements, that's 1 here and 5 here. Change sign of non-diagonal elements. And into matrix C, we have matrix C, then 1 and 3. Let's multiply. It's 1 minus 4, minus 2 minus 12. It's minus 1 plus 5. Then 2 plus 5 into 3, 15. This is 17. This is the unknown matrix. Question A is given, and also given is A transpose is A inverse. We have to find values of x, y, and z. So this is given A transpose. We multiply, post multiply both sides by A. Post multiplication is multiplication to the right of matrix. That's A transpose into A is A inverse into A. This is post multiplication, multiplication to the right. A transpose into A. A inverse into A is by definition I. Let's substitute values. A transpose, interchange rows and columns. X, this is minus y and z, into A, this is A, 0 to y, z, elements of the first row, second row, this is third row, is equal to I. I is unit matrix, also called identity matrix. 0, 1, 0 and 0, 0, 1. Let's multiply. 0 plus x square plus x square. This is 0 plus xy minus xy. 0 minus xz plus xz. Elements of the first row. Right hand side we have 1 0 0. Next, this into this is 0 plus xy minus xy, 4y square plus y square plus y square, that is 6y square. 2yz minus yz minus yz, this is 0. This is 0 minus xz plus xz. This is 2yz minus yz minus yz, this is 0. Z square plus z square plus z square, that's 3z square. This is 0, 1, 0, 0, 0 and 1. Now from definition of equality of matrices, so we know the corresponding elements are equal, that is 2x square is 1 or x is plus minus 1 by root 2. Similarly, 6y square is 1 means y is equal to plus minus root of 1 by 6 and z is plus minus 1 by root of 3. From 3z square is equal to 1. Okay. We are given this matrix equation. This is equal to right hand side. Unknown matrix B. This is where to find out. Let's say this matrix is A. We have B. Let's say this is C and this is D. So this is the matrix equation. And from this we have to find out B. We can have B if we remove A from left hand side and also C from the right hand side. To remove A from left hand side, we pre-multiply both sides by pre-multiplication, I repeat, is multiplication to the left. Pre-multiply both sides by A inverse. Let's see what do we have. A inverse into A into B into C is A inverse into D. A inverse into A is I. And I into B, identity matrix into matrices, the matrix. That's B. B into C is A inverse into B. So we are able to eliminate A from left. We have now BC equal to this. We'll have B if now we eliminate C from right. For that, we post multiply. Post multiply by C inverse. That is, we have B into C inverse. So do not change order because we know product is not commutative. C into C inverse is I, so this is B into I and this is B. A inverse into D into C inverse. We can find out this product and that will be B. For A inverse, let's check what is determinant of A. It's 3 into 5, 15 minus 7 into 2, 14, not equal to 0. So this is 1 by determinant into adjoint of A. Adjoint means interchange the diagonal elements, change sign of these. Then we have matrix D, the given matrix 2, this is minus 1, this is 0 and this is 4. C inverse, this is C. Let's check what is determinant of C. It's minus 1 plus 2, this is also 1. So we have 1 by determinant of C into adjoint of C. Again, interchange the diagonal elements, change sign of these. So now we can multiply. So we know matrix multiplication is associative. That means we can multiply this with this and resultant by this, or we can first of all multiply these two and then multiply this. So this is 5 into 2, 10. This is minus 5 minus 8. This is minus 14, then 7 plus 12, this is 19, into 1 minus 1, then 2 minus 1. That's 10 minus 26, minus 10 plus 13, minus 14 plus 38, plus 24, and 14 minus 19, this is minus 5. This is matrix B.